アシュクロフトマーミン始めます。で、日にちを変えます。そっか。今日は6時15分でいいか。7時15分。それで、そっか、こうやらなきゃ。また音がでかくなってきた。18。はい、それからコンパス12、これ30分後だけど6時半でいいか。じゃあ6時半でいいかな。そしたら、ここにテキストがあります。それでダウンロードします。AC コンダクティビティをやってました。それで、プラズマフリークエンシーまで行きました。で、プラズマフリークエンシー、サイクロトロンフリークエンシー。サイクロトロンフリークエンシーは、EHMC でしょ。それから、プラズマフリークエンシーはこれ でもう一つね、リラクゼーションタイプ、これがあるでしょ。タウ分の1。So, I hope there will be a comparison between these three. When is real negative, epsilon is real or negative. Epsilon is negative means real and negative means omega square. This is omega is smaller than plasma frequency. The solution to 134 decay exponentially in space. No radiation can propagate. However, when epsilon is positive, frequency of electromagnetic wave is larger than plasma frequency. The solution to 134 becomes oscillatory. Radiation can propagate and the metal should become transparent. This condition is only valid, of course, in our high frequency assumption is satisfied. 136. This is satisfied. High frequency assumption is satisfied. In the neighborhood of omega equal omega p. If we express tau in terms of the resistivity through equation 1.8, then we can use the definition 1.38 of the plasma frequency to compute that. Plasma frequency omega p tau equal 1.6 times 10 to 2. I think we did this. This is a micro ohm centimeter. This is micro ohm centimeter inverse. Since the resistivity in micro ohm centimeter, rho u is of the order of unity or less, and since Rs divided by A0 is in the range 2 to 6, the high frequency condition 1.36 will be well satisfied. Why? At plasma frequency. The alkaline metals have in fact been observed to become transparent in the ultraviolet. Alkali metals have in fact been observed to become transparent in the ultraviolet. A numerical evaluation of 1.38 gives the frequency at which transparency should set in as nu p equal omega p divided by 2 pi equal 11.4 times Rs divided by A0 to the power of minus 3 half times 10 to 15 Hertz. 10 to 15 Hertz. Or lambda p equals c over nu p equals 0.25. Rs divided by A0 to the power 3 half times 1000 angstrom. This is like 10 to 2 nanometer. This is like 26 something like this. Maybe 20, 30, 40 nanometer. In table 1.5, we list the threshold wavelengths calculated from 141 along with the observed threshold. Okay, along with observed threshold. Observed and theoretical wavelengths below which the alkali metals become transparent. D2 theoretical lambda is 1500 angstrom. Observed lambda is 2000 angstrom. Hey, this is very big. Rs divided by A0. This is 2 to 6. Because this value is 2 to 6. Anyway. Okay. Sodium 2.0 or 2.1, potassium 2.8, 3.1, rubidium 3.1, 3.6, cesium 3.5, 4.4. The agreement between theory and experiment is rather good. As we shall see, the actual dielectric constant of a metal is far more complicated than 137, and it is to some extent a piece of good fortune that the alkali metals so strikingly display this druid behavior. In other metals, different contribution to the dielectric constant. In other metals, different contribution to the dielectric constant compete quite substantially with the druid term 137. Second important consequence 137. What was 137? So 137 is epsilon, epsilon omega equal 1 minus omega p square divided by omega square. A second important consequence of 137 is that the electron gas can sustain charge density oscillations. By this, we mean a disturbance in which the electric charge density has an oscillatory time dependence exponential minus I omega t from the equation of continuity. Say this is difficult. Equation of continuity. This is the equation of continuity. Let's see, footnote 22. Footnote 20. The charge density rho should not be confused with the resistivity, also generally denoted by rho. The context will always make it clear which is being referred to. Okay, so equation of continuity is this. Then we consider a Fourier transform somehow. Then we obtain this. If we consider Fourier transform, this becomes this. Then, and Gauss's law is this. We find in view of 130 that, let's go back to 130. J sigma E is this 130 J omega E sigma omega E omega. How do we get it? So probably we should put it here, right? So delta divergence of this divergence, this is a vector, this is vector. So divergence of that is sigma omega divergence of E. Divergence of E is 4 pi rho omega. So this one is this. Four pi sigma omega rho omega. This has a solution provided that one plus what's this? Okay, I can do I omega minus 4 pi sigma omega I omega minus 4 pi sigma omega rho omega equals 0. So this part, this has to be 0. If this is 0, this is not 0. So this has a solution provided that 1 plus 4 pi I sigma divided by omega equals 0, which is precisely the condition we found above for the onset of propagation of radiation. Is that right? Four pi I sigma. I got confused. 4 pi I sigma y sigma omega sigma omega this one. Okay. Which is precisely the condition we found for the concept of propagation radiation. The present context, in the present context, it emerges as the conduction. The frequency must meet if a charge density wave is to propagate. In the present context, it emerges as a condition the frequency must meet if a charge density wave is to propagate. The nature of this charge density wave, known as a plasma oscillation or plasmon, can be understood in terms of a very simple model. 23. Since the field of uniform plane of charge is independent of the distance from the plane, this crude argument, which places all of the charge density on two opposite surfaces, is not as crude as it appears at first glance. Anyway, imagine displacing the entire electron gas as a whole through a distance d with respect to the fixed positive background of ions. Figure 1.5. The resulting surface charge gives rise to an electric field of magnitude 4 pi sigma, where sigma is the charge per unit area at either end of the slab. Since the field of uniform plane of charge is independent of the distance, uniform plane of charge is independent of the distance from the plane. Field of a uniform plane of charge is independent of the distance from the plane. This crude argument, which places all the charge density on two opposite surfaces, is not as crude as it appears at first glance. Number 24. We observed earlier that the Drude model does take the electron-ion interaction into account by acknowledging that the attraction to the positively charged ions confines the electrons to the interior of the metal. In this simple model of plasma oscillation, it is precisely this attraction that provides the restoring force. Number 25. Surface charge density sigma should not be confused with the conductivity, also generally denoted by sigma. At either end of the stop. Simple model of plasma oscillation. N electrons. N divided by Z ions. E is 4 pi n dE. Sigma equal plus n dE. Right hand side. Sigma equal minus n dE. Consequently, the electron gas as a whole will obey the equation of motion nm d dot dot equal n minus ne 4 pi sigma absolute value equal minus ne 4 pi nde equal minus 4 pi ne square nd, which leads to oscillation at plasma frequency. Yeah. I don't know how we can build this equation. Electric field of 4 pi sigma. This is the electric field. Okay, which leads to plasma with the oscillation at the plasma frequency. Few direct observations have been made of plasmons. Perhaps the most notable is the observation of energy losses in multiples of h bar omega p when electrons are fired through thin metallic films. 26. How do you fire electron? Perhaps the most notable is the observation of energy losses. I don't understand. Perhaps the most notable is the observation of energy losses. Energy loss. Energy losses in multiples of h bar omega p when electrons are fired through thin metallic fields. Nevertheless, the possibility of their excitation in the course of other electronic processes must always be borne in mind. Nevertheless, the possibility of their excitation in the course of other electronic processes must always be borne in mind. Okay. Thermal conductivity of a metal. The most impressive success of the Drude model at the time it was proposed was its explanation of the empirical law of Wiedemann and Franz, 1853. The Wiedemann-Franz law states that the ratio kappa divided by sigma of the thermal to electrical conductivity of a great number of metals is directly proportional to the temperature with a proportionality constant which is to a fair accuracy the same for all metals. This remarkable regularity can be seen in table 1.6 where measured thermal conductivities are given for several metals at 273 K and 373 K along with the ratio kappa divided by sigma T known as the Lorentz number at two temperatures. In accounting for this, the Drude model assumes that the bulk of the thermal current in a metal is carried by the conduction electrons. This assumption is based on the empirical observation that metals conduct heat much better than insulators do. Thus, thermal conduction by the ions present in both metals and insulators is much less important than thermal conduction by the conduction electrons present only in metals. 27. Although the metallic ions cannot wander through the metal, there is a way in which they can transport thermal energy, though not electric charge. The ions can vibrate a little about their mean position, leading to the transmission of thermal energy in the form of elastic waves propagating through the network of ions. See chapter 25. To define and estimate the thermal conductivity, consider a metal bar along with the temperature varies. To define and estimate the thermal conductivity, consider a metal bar along which the temperature varies slowly. If there were no sources and sinks of heat at the ends of the bar to maintain the temperature gradient. If there were no sources and sinks of heat at the ends of the bars to maintain the temperature gradient, then the hot end would cool and the cool end would warm. That is, thermal energy would flow in a sense opposite to the temperature gradient. Let me see. If there are no sources and sinks of heat at the end of the bar to maintain the temperature gradient, then the hot end would cool and the cool end would warm. That is, thermal energy would flow in a sense opposite to the temperature gradient by supplying heat to the hot end, and as fast as it flows away, one can produce a steady state. If there were no sources and sinks of heat at the end of the bar to maintain the temperature gradient, then the hot end would cool and cool end would warm. That is, thermal energy would flow in a sense opposite to the temperature gradient by supplying heat temperature gradient. So this is a break here. Break. By supplying heat to the hot end, as fast as it flows away, one can produce a steady state in which both a temperature gradient and a uniform flow of thermal energy are present. We define the thermal current density JQ to be a vector parallel to the direction of heat flow. whose magnitude gives the thermal energy per unit time crossing a unit area perpendicular to flow. 2080. Note the analogy to the definition of electrical current density J, as well as the analogy between the Ohm's laws of Ohm and Fourier. Ohm and Fourier. Why Fourier? For small temperature gradients, the thermal current is observed to be proportional to nabla T. Fourier's law. Q equal minus kappa nabla T. The proportionality constant kappa is known as thermal conductivity and is positive. Since the thermal current flows opposite to the direction of the temperature gradient. Experimental thermal conductivity and Lorentz numbers of selected metals. Kappa thermal conductivity, kappa watt per centimeter Kelvin. So copper, silver has large thermal conductivity, copper and silver, gold, beryllium, aluminum has very large thermal conductivity, but all metals, Lorentz number is almost 2.2. Niobium a little deviate. Niobium and iron, cadmium, thallium, bismuth, antimony, tin, indium. I think these metals kind of deviate from the regular Lorentz number value. Lorentz number value is 2.2 times 10 to minus 8 watt ohm divided by Kelvin square. As a concrete example, let us examine a case where the temperature drop is uniform in the positive x direction. In the steady state, thermal current will also flow in the x direction and have a magnitude JQ equal minus kappa del T del X. To calculate the thermal current, we note assumption 4, page 6, that after each collision, an electron emerges with a speed appropriate to the local temperature. The hotter the place of the collision, the more energetic the emerging electron. Consequently, even though the mean electronic velocity at a point may vanish, in contrast to the case when an electric current flows, electron arriving at the point from the high temperature side will have higher energies than those arriving from the low temperature side, leading to a net flow of thermal energy toward the low temperature side. figure 1.6 with 1.6. Okay, figure 1.6. How much do we have? This is pretty much. Okay. Figure 1.6. Schematic view of the relation between temperature gradient and thermal current. Electrons arriving at the center of the bar from the left had their last collision in the high temperature region. Those arriving at the center from the right had their last collision in the low temperature region. Hence, electrons moving to the right at the center of the bar tend to be more energetic than those moving to the left, yielding a net thermal current to the right. Complicated. I think this is complicated. I think let me stop here. This is what page? 21. I stop.